Hello friends, we have so far been considering different types of functions and their derivatives. So we began our discussion with something called as univariate functions. So what this distinguishing feature about, or what is the characteristic feature of this univariate functions, is that this function is principally governed by a single independent variable. So if you relate this function or treat this function as a variable itself, then y becomes the dependent variable, and this dependent variable is dictated by the value of this dependent variable. The value of this dependent variable assumes is dictated by a single independent variable. Now we also saw that in addition to the univariate function, we can also have a bivariate function, wherein the function is dependent on two variables, which is influenced by two variables. The way we handle these functions, particularly when we say we handle or we want to consider the derivative of this function, it varies depending on what are we dealing with or what essentially these functions relate to. Now, when we consider this univariate function to represent the free energy of a unary system, when this univariate function, when it represents the free energy of a unary system, the way we handled the derivative of this function was quite different from how we handle a generalized univariate function. Let me repeat, we have a univariate function and we attributed this univariate function. We said that this univariate function is discussing about, or it rather describes, the free energy of a unary system. That understanding helped us to handle this particular function in a different manner as opposed to a conventional approach. In case of bivariate function, when we attributed or when we referred to this function as one that describes the free energy of a binary system, our understanding of a closed binary system, our understanding of how a closed binary system behaves, allowed us to reduce these two so-called independent variable to one. So what essentially we have done is, there are conventional ways of handling univariate and bivariate functions. Particularly, there are conventional ways of taking the derivative of the univariate and bivariate functions, but our understanding of the system that we are dealing with, our understanding of the material, or our understanding of the metallurgical and materials concept allowed us to handle these functions, these seemingly different functions, in a unique way. So that is what essentially the crux of this course is all about. So just the understanding of the numerical concept or the mathematical concepts alone, it could get us so far, but there is a limit to it. Just the understanding of the metallurgical behavior and the metallurgical concepts alone will get you thus far, and there is a limit to it. What essentially we are trying to do is, we are trying to combine these two, and then we are trying to make the generalized numerical approaches, generalized mathematical approaches, specific to our problem of interest. So we are trying to make or fine tune or refine the existing approaches specific to address our problem. So that is what essentially the materials research which involves numerical technique is all about. You have a generalized framework that is established by mathematicians per se. What we try to do is, we try to refine, fine tune it, we try to make some assumptions that are relevant, that are consistent with the material we observe, and then we try to use, or we try to reformulate the existing approach and adapt for our model, or adapt for describing our system. So that is essentially what we did when we considered the binary system. We had an understanding of what a binary system is, particularly what a closed binary system is. That understanding, using that understanding, we were able to reduce a bivariate function to univariate function without losing any critical aspects, without losing any generality, without losing any component that would distort the nature of the function. So we were able to, even though we were able to reduce the dimensionality, we did not compromise on the nature of the function. This was possible primarily because of our understanding of the material system that we are dealing with. So essentially, numerical techniques in material research involves this, wherein we try to relate our generalized understanding of the mathematical concepts to that of our insights, our knowledge that we have gained, the domain knowledge, so to speak, and we try to refine or we reformulate the generalized approach so that it can be used in our specific, it can be used to describe our specific system, our specific behavior that we observe in our system. Now, when we consider this bivariate, so apart from this unary function or a unary system, the function that describes the free energy of the unary system, when you move away from such a system, in most cases, the univariate function, the derivative of the univariate function, it largely assumes a constant value. Let me repeat, when you remove the assumption of, when you move away from the assumption of unary system and you are discussing about the free energy of largely a binary system, in those cases, the function that describes the free energy of the binary system for those functions, very rarely the derivative is of a constant value. So what essentially would be the nature of the derivative in such cases is the derivative as well will depend on the value the independent variable assumes. So let me repeat, when you move away from the unary systems, when you consider binary systems, and again both these have the free energy described using univariate functions. So both unary and binary systems, their functions, the free energies of these systems are described using univariate functions. So, but when you move away from the univariate systems and when you largely focus on the binary system, the derivative of this univariate function that describes the free energy is rarely a constant. But on the other hand, what would be the nature of this derivative is, this derivative will be dependent on the value the independent variable assumes. So when you write it down, so the derivative of the free energy function, so this function, now it pertains to a binary system. It is no longer we are considering a unary system, we are considering a binary system. So in case of a binary system, we assume that this C here for a closed system, we can the total number of components in the closed system, the total number of atoms that constitute a closed system is equal. So what we have done is that allowed us to reduce the number of independent variables that is involved. So in binary systems, there are two independent variables. Supposing if you take the example of carbon and iron that make steel, in a closed system, there is a definite proportion of carbon present and a definite proportion of iron present. And this definite proportion, there is a definite fraction of carbon present and there is a definite fraction of iron present. So this fraction of carbon and iron, particularly when the amount of carbon is expressed in terms of mole and the amount of iron is expressed in terms of mole, this fraction of carbon that is present and the fraction of iron that is present is expressed in terms of mole fraction. So the reason why we are considering mole fraction, or why generally when you refer to any research article, the concentration is often treated in mole fraction, is because there are primarily two reasons. One is you have an elegant way of relating the concentration of one component to the concentration of other component in a binary system. So we have taken our example as steel to be a binary system. It comprises of carbon and iron. Now when you express the concentration of steel, this mild steel that comprises of just carbon and so plain carbon steel which comprises of just carbon and iron and which is present in a closed system, when you describe the concentration of the steel in mole fraction, it is possible for us to express the combination of the concentration as this. So when you are able to express the concentration of a given closed system in using rather mole fraction, then you will be able to relate the concentration of the components that are present in the system. In case of binary, we have carbon and iron, so their concentration can be represented in this manner. So it means the concentration of carbon and the concentration of iron, they are dependent, and this is rather an elegant representation of the relation that exists between the concentration of carbon and iron. Secondly, one other reason why mole fraction is largely adopted in numerical treatment of concentration is because it has no unit. So if you could recollect the mole fraction, the expression for the mole fraction, particularly if you consider the mole fraction of carbon, it can be expressed as the number of moles of carbon that is present by number of moles of carbon and the sum of the number of moles of carbon and number of moles of iron. So total number of moles of a component atoms that are present will be assumed as the denominator, and the numerator, the number of moles of our desired component will be taken. So here the numerator will assume the value of moles, and the denominator will also assume the value of moles. So therefore the moles get cancelled out, and ultimately, so the unit will be moles, and the denominator will also assume a value of moles. They get cancelled out, and ultimately you end up with a dimensionless quantity or a dimensionless parameter to describe the concentration. So therefore the mole fraction is adopted to treat concentration in numerical techniques. So whenever there is a possibility of handling a parameter without dimensions associated with it, you would often go for that parameter while you are handling it in a theoretical framework. So that is something that you might experience while you are doing research. But if given a choice, it is always best for us to go for a parameter that has no unit associated with it. That will make our process, or that will make our formulation a bit more straightforward. So this is the reason why we go for mole fraction. That is, it offers an elegant relation between the components that are present in the system, and secondly, there is no unit associated with this way of describing the concentration of the material. Now, this is just not this relation is not exclusively associated with a binary system. This relation can be extended for any number of systems. So it can be extended for, say, a system with k components, and for the system with k components meaning you have one base metal and several other alloying elements associated with it, which is generally the case, which is generally what you observe in an application. In such a case, when you use mole fraction to describe the concentration of the different components, the different elements that are present in a given system, then it is also possible for us to express that relation between each of these concentration in this manner. So if you say your system has 1, 2, and so on and so forth till k component, this relation still holds true. Rather a convoluted way of writing it would be something like this. And all that it means is that the mole fraction of 1, mole fraction of 2, so 1 and 2 are the individual alloying elements or the base metal, and ultimately sum of all the concentration of the individual elements that are present in a multi-component system will be of this form here. Now this relation, again, it helps us in reducing the dimensionality of the system, meaning when we are handling such a system, we don't have the need to consider all the key components separately, but this relation allows us to handle only k minus 1 components. So expressing the concentration in mole fraction, particularly, again, this all is in the context of closed system. When we have a closed system and we are handling either binary, ternary, or whatever may be the nature of the system, whatever may be the number of components that are associated with the system, owing to the nature of the closed nature of the system, it is possible for us to reduce the number of independent variables by 1. So if you have a system that has k components associated with it, it is possible for us to reduce it to k minus 1 independent variables. So that's the reason why, even though the free energy of a binary system is dependent on, or it can be described, or it should be described using a bivariate function, we were able to reduce it to a univariate function. Now, getting back to our, so this is just some side note that might be helpful for your understanding of certain materials research, wherein you would notice when they talk about expressing the concentration of in mole fraction, they ultimately assume that even though the system comprises of k minus k components, they assume that there are only k minus 1 independent variables present. The reason why they are able to assume such make such reasonable assumption, that consistent assumption, is primarily because they have expressed it in terms of the mole fraction, and again they are considering a closed system. So whenever you are looking into literature, research literature, and you find that despite stating that there are k components involved in the system, their expression only involves k minus 1 components, it's primarily because they have reduced this dimension based on our understanding of what a closed system is. Now, when you are considering a binary system, the free energy of the binary system, that is dependent on one of the variables. So even though it is influenced by both the concentration, now that we have expressed a relation between these concentration, now it is dependent on one of the independent variable, one of the concentration. Now, in most cases, in generalized case, what we observe is the derivative of this free energy, which is the chemical potential, it varies with the value of the concentration. It is also dependent on concentration. Depending on what is the value of the concentration, the chemical potential also varies. So when we try to plot the free energy curve, for instance, so let us take a random example, a generalized example, something of this sort. A little bit more easier, something of this sort. Now, when you consider this is the free energy and this is the concentration and this is the independent concentration, one independent concentration in the binary system. Often the independent concentration that is chosen is the concentration of the alloying element, the concentration of the base metal or the matrix. It is always taken as the independent variable. So in this case, it is often the concentration of carbon that is taken as the independent variable. So in this case, we have a generalized case wherein we have free energy of a binary system that is dependent on and one independent concentration. Now, when you consider the derivative of this function at this point here, so it is expressed as in this way. So derivative of this function here, it is different from the derivative of this function at this spot here. So the derivative, it is expressed as this, and this derivative we saw, it is nothing but the slope of a given function. So in our previous discussion, we were able to relate to what this derivative means geometrically, and this derivative, again, this you have been much familiar with. So this derivative, it varies when you consider these 2 points here. So the derivative at this point is much different from the derivative at this point. In those instances, there is a way of representing, or there is a way of describing these derivative or these slopes, or in our case, in this case, in the context that we are considering, the chemical potential at these different concentration. In thermodynamics, when you are looking at literatures that involve thermodynamics, the derivative at this spot is expressed by, of course, we have this conventional representation dfc by dc, so df by dc. So, but we are not talking about a generalized derivative. We are not talking about the function of this derivative. This we are not talking about. We are not treating this derivative as a function. We are not doing that. We are not treating this derivative as a function, but we are talking about a derivative at the specific point, say C1. So in that case, the way at this point the derivative is a constant. So the way this constant derivative is represented is of this sort. So what this means is that we have a function, we have a free energy function, and we are considering the derivative of a function at a specific concentration of C1. And since we are focusing on a specific concentration, this derivative, even though it can be a function, it assumes a constant value. The same goes for this part here. So it will be df by dc, see, assuming the value of C2, considering that this point is C2. So what we have done is, so what we have essentially considered is the free energy function. In most cases, the nature of the free energy functions is such a way that the derivative of the free energy function, the derivative of this free energy function are in themselves dependent on the concentration. However, in some cases, we might be interested in understanding what is the derivative of the free energy function at a given spot. So when you are doing that, in those cases, then the way we represent the derivative of the free energy function at a given spot is something of this sort, wherein C1 is our desired spot. So this can be C1, C2, and so on. And in this case, this is no longer a function, but a constant value. Now, getting back to the graphical representation that we have considered. So here we have considered two spots, that is C1 and C2, and we have stated that the slope at this point is much different from the slope at this point. So what could be the reason for it? We just started from our argument, or we started our discussion by stating that the slope at this point is different from the slope at this point. Why it is? What is the principal difference that we observe when you consider the slope at, say, C1 and the slope at C2? Now this understanding can also be gained by considering our expression for our rather the expression that we are considered for that yields us the derivative of the given function. So derivative of the given function is nothing but how a function changes as the independent variables that are associated with it changes. So therefore we have free energy function, and what we want to know is how as the concentration changes, how as the concentration of the alloying element changes. Now again, it is important for us to use the materials related term when we are describing this function. It is not just x and y or dependent or independent variable. Even though we are acquainted with the term, we have to familiarize ourselves, we have to get acquainted with those terms. It is important for us to, in our discussion, to use these metallurgy or material related terms. So therefore in this case, even though what I essentially want to know is the derivative of the free energy with respect to concentration is how the free energy changes as the concentration changes. Now what we are interested is in not the derivative as a function but as a constant value, because we are focusing on a specific concentration C1. So in that case, what we essentially have is we have the function at C1 plus delta T minus the value of the free energy at C1 divided by delta C. So we want to take the derivative of the function at C1, and we have arrived at this expression here. So this is rather we have expressed the generalized formulation of derivative as a function that we are interested in. We have included our desired concentration to it, and we have expressed the variable in such a manner that it indicates concentration. So there is a generalized formulation and which we have expressed as d. So this is the generalized formulation. So a generalized formulation would look something like this. This we have seen in our introductory lectures. Now what has changed when we are expressing it in this manner? We have considered a condition, a specific condition. We are not treating the derivative as a function. We are no longer treating it as a function. So we have considered a specific condition, and based on this condition we have reformulated, or we have expressed the relation or the description of the derivative based on this condition here. So therefore the point that we are interested in, the x that we are interested in, the concentration that we are interested in is mentioned here. The change in the free energy as we move away from this desired concentration is expressed in terms of the delta C, and that is considered as the numerator. So this is a generalized description of the derivative of a given function. So here what we are considering is a derivative of a free energy function at a specific concentration, and in order to denote that we have expressed the relation of the derivative in this manner. Now let us go back to the graphical representation. So instead of going back to it, since it's a rather a curve that can be drawn, so we are considering, we have redrawn it here. So our point is C1 here. So this is the point of our interest is C1 here. So this is what we are focusing on. Now if you look closely, the value of the free energy as you move away from this point. So if you move away from this point, say from C1 to this point, C1 plus delta C. So when you move away from this point here to the subsequent point here, and this point is C1 plus delta C. When you move from the red to blue point, what essentially you observe is the corresponding free energy, that is f of C1 plus delta C is less than f of C1. So what we have done is, in order to understand how the free energy changes as the concentration value varies, you have considered 2 points. The C1 is the concentration of our interest, and you have moved away from C1 and you have evaluated its free energy. Now for this nature of the curve at C1, as you move away from C1, the free energy decreases when compared to the original position. So red here is the original free energy, that is f of C1, and f of C1 plus delta C is the blue one here. And as you can see, what has essentially happened is, as you can see, the value of the free energy has reduced. So when you substitute, or when you consider this relation that you have observed from the curve, when you consider this relation that you have observed, what you end up having is, if you substitute it here, what you end up having it is at C1, the derivative of the function at C1 is less than 0, because the first term here, that is in blue, that is indicated in blue, is less than the second term that is indicated in red. So therefore, the numerator will assume a negative value, and delta C is the change in the concentration. So therefore, it assumes a positive value. So therefore, at C1, at the concentration that we desire, the derivative assumes a negative value. The derivative is of negative value. So what it means is that at C1, the slope is negative. So one way of describing how the chemical potential, or how the derivative at a given concentration is, one way of describing is by considering just the positive, how it is in relation to 0. Is it greater than 0, or is it negative, less than 0? So in this case, at C1, what we observe is the derivative is less than 0. So therefore, the slope at this particular concentration C1 is less than 0. So what essentially we have is, at C1, we have a negative slope. So the first derivative, the derivative of the free energy function at C1 is negative. Now let us consider another point. Let me use green. So let us consider another point like we have considered before, and let us assume it to be C2. Now the free energy function, or the derivative function expression for the free energy at C2 can be expressed as, so this is what the expression for the derivative of the free energy function at C2 would look like. So the free energy at C2 plus in a position away from it, minus the free energy function, or the free energy at C2. In the denominator, we have the distance separating our original position and the position that we have considered to estimate the derivative. So what we have done is similar to what we have considered. So we have repeated what we essentially, the treatment we adopted for the derivative in case of the concentration 1. Now in case of concentration 2, all the approach is minus the same. We have considered a point that is separated by delta C, and we have taken the free energy at that new point, subtracted it from the original free energy, and we have taken its ratio with respect to that of the difference that separates the point and the original point, the moved away point and the original point. Now when you do that, so when you move away from the C2 by delta x, and you take up a position here, so this is C2 plus delta C, it is possible for us to note that the free energy at C2, so the green one is the free energy at C2, and the grey one is the free energy at the subsequent point. So what we observe at C2 is the free energy at C2 is less than the free energy at the subsequent point, that is C2 plus delta C. So the free energy at the subsequent point is greater than the free energy at the original point. So it means this subtraction, or this value here, the derivative at C2, when you treat this, adopt those values and substitute it in this expression, what we observe is, under this condition, when the free energy at the original point and the free energy at the point C2 is less than the free energy at the subsequent point, what we observe is the first derivative of it is greater than 0. So ultimately what we end up having is a positive slope. So what this description of free energy at the various points, what they indicate essentially is, one, generally when we are describing the free energy of a function, or rather a free energy of a binary system, the derivative of it is rarely a constant, and the derivative of it varies with the independent variable. So the derivative, the chemical potential, it also varies with the concentration. Not only the value of the derivative varies, but also the sign associated with it, the nature of the derivative also varies. So as we have seen in this case of C1, we have, it is for the same free energy function. At one point what you observe is a negative slope, and the other point what you observe is the positive slope. So here we have not given a definition. Okay, when you say derivative is negative, it's a negative slope. When you say derivative is a positive, it's a positive slope. We have not taken any such assumptions. From the first principle expression of these expressions, these generalized expression that helps us understand what a derivative is, so these are referred to as the first principle expressions. So these are first principle. We have not dogmatically, we have not assumed an axiom that okay, when the derivative is negative, it's a negative slope, when the derivative is positive, it's a positive. We did not rather start from that presumption. What we essentially did is we began with this description of, again this description is nothing more than a numerical way of expressing what a derivative is all about. Arriving at this expression, we did not go through complicated process. All this expression means is what essentially the description for a derivative is. From that we were able to arrive at this expression, arrive at this relation. Now using this relation, we were able to show that there is a difference in the derivative for a given free energy function. This difference in the derivative need not always be a quantitative, what is the value the derivative assumes, what is the value the chemical potential assumes. It can also be along the signs of the derivative. It can be positive derivative, it can be negative derivative. The derivative that we can estimate can be positive and cannot be negative. And these values relate to the positive and negative slope of the curve. So all this we were able to arrive at from a generalized way of describing a function and a generalized way of describing the derivative of a function. Now in all these discussions, what we have, when you consider the expression, the generalized description of the derivative, so the way we arrived at this is rather straightforward. All we wanted to do was we wanted to see how a function changes as the independent variable changes. So the denominator considers the change in the independent variable, and the numerator it considers how the function itself changes as this independent variable that dictates the function varies. That is all this relation is all about. Now what we have, while considering what, there is a specific convention that we have adopted. So implicitly we have adopted a specific convention while we are describing the derivative of the function. What is the convention involved is when considering the next point. So we are assuming there is a change in the independent variable, and when considering this change in the independent variable, we assumed that this independent variable, this change is rather moving forward. Meaning, so far what we have assumed is, so this is our function, a section of our function, and now we want to see how at this point C1. So let us have a generalized description now, the generalized discussion here. So we have a function f of x that is dependent solely on x, and we want to know what is the derivative at x1, and in order to do that we consider a subsequent point, and this subsequent point we have so far assumed to be a point that is subsequent. So we have a linear increase in x1, so this x1 it linearly increases in this direction, so it increases in this direction. So what we have done is we have considered the subsequent point, we have considered the change in the positive direction. So along this direction, along the right hand side direction to me, we have considered the change. So that yielded us the point here. That yielded us a point here which is separated by delta x. And using this expression here, we were able to calculate, so far we were able to calculate the derivative at this position x1. So what it means so far is that we are considering a position, and so far we have considered a position, a given x value and a subsequent value that is along the right hand side of your axis, that is progressively increasing. So the next position that we have thus far considered is a progressively increasing one. So what it means is that x1 plus delta x is greater than x1. So this is what we have assumed. If you treat this as x2, or this is just x1 plus x1 plus delta x, this is greater than x because we are moving in the positive direction. So that is what we have so far been considering. So we have considered a forward variation in the independent variable, and that is what yields us this expression here. So we have considered a forward variation, meaning a forward increase in the our initial point that we are interested in, that is x1, and based on this forward increase, we considered what is the change in the function, what is the change in the f of x, that assumes the numerator, and the forward change in the independent variable assumes the denominator. Now it is also possible, so this is what we have been considering so far. So we have considered the points, and we have considered the subsequent point to be a point that is in the forward direction, that is greater than our initial point, and based on that assumption and based on that consideration, we were able to express the derivative of a given function. Now it is also possible for us to consider a point that is less than our desired function. So let me repeat. So far we have the points that we have been considering is, say, if we are the point of our interest is x1, the point that we have considered to express or to identify, to calculate its derivative is x1 plus delta x, and so far this relation has been satisfied, that is the next point is always greater than our initial point. Now it is also possible for us to have another point which is less than our desired point. Now what we are in this case doing is, we are considering a point that is less than our desired point. So this point here, now we are considering, and this point is x1 minus delta x. So we have 2 points, one in red and say other in green. So far we have been considering the green one, wherein the next point is x1 plus delta x. However, it is also possible for us to consider this point here, that is x1 minus delta x. Now let us see how the formulation for the generalized formulation for the derivative of the function changes when we are considering a point that is behind the point of our interest. So this point, the green one, is a point that is in the forward direction, and this one is behind our, so the point in red is behind our desired point. Now when we want to find the derivative of the function by considering a point that is behind our desired point, the expression for the derivative changes in this manner. The expression for the derivative changes in this. So what we observe is, when we are considering, so when we relate the function here to that of the function here, what we observe is, in the first description of the derivative, the f of x assumes the it takes the place of the second term. In case of this description, the f of x takes up the place of the first term in the numerator. So f of x is in the numerator. The similarity is, there is delta x, the similar delta x found in both the cases. We have delta x in both the cases that assume the role of the denominator. However, the key difference is that in the numerator, the functions, they take a reversed position. They take a reversed position. In case of, when you are considering a point, an independent variable that is greater than our original variable or original value, in that case, the free energy of the new position takes up the first term, and the free energy of the original position takes the next term. However, in this case, when you are considering a position that is less than the original position, in that case what we observe is, the free energy of the original position take up the first term or assumes the first term, and the free energy of the newly directed position takes up the second term. So when we are considering this expression for the derivative, there is a convention associated with it, that is the rightmost term, the independent value of the higher magnitude, the corresponding function takes the position of the first term. So here x plus delta x is greater than x. x plus delta x is greater than x. So therefore, the corresponding free energy of the x plus delta x assumes the first term. In the same way, in the second case, in this case here, x is greater than x minus delta x. So therefore, the corresponding free energy takes up the first term. Now, when you then consider the derivative at x1 using both these expressions, you will notice that the sign of the derivative remains the same. So what we essentially have is, we have expressed the derivative of the function in two ways. In one of the way we have in one of the formulation we have considered a point that is greater than the original point, and this we expressed in this manner. In another formulation we have considered a point that is less than the initial point or the original point, and the expression correspondingly changes to this. Now what we observe is, here the free energy function of the point that we have considered besides the original point, as you can see, is the green one here, and it is less than the f of x. And here, if you can compare the free energy function of the original point, that is x1, so it is here, and the free energy function of the point that we have considered is here. So this is the free energy function of the point that we have considered, that is f of x minus delta x. So what we observe is, the f of x is less than f of x minus delta x. So if you consider the plot that we have, let me redraw the plot that we have looked or that we are considering. So here we have our desired point x, and here this point is x plus delta x, and this point here is x minus delta x. Now the free energy of, so let us use red, the free energy of x minus delta x is here. The free energy of f of x is here, and finally the free energy of x plus delta x is here. So this is x plus delta x, and this is x minus or f of x, and this is f of x minus delta x. And what we observe is this relation, that is f of x plus delta x is less than f of x, and f of x is less than f of x minus delta x. Now when you substitute these values, when you consider this relation, in the context of the above expression here, we notice that both the derivatives, so in this case and also in this case, so in this case forward case and also in the reverse or the backward case, both this expression give us a value, a derivative that is less than 0. So what we ultimately end up having is, we have a derivative that is at least quantitatively or rather qualitatively identical. Now of course, when you introduce the limit that delta x tends to 0, it will also be quantitatively accurate. But just from the description, just from the generalized description of the derivative, we are able to state that there are two ways of expressing it, and in both these approaches, we are able to qualitatively arrive at the same derivative. We can either consider the forward point or either consider the reverse or the backward point. In both these cases, either even if you are considering a forward point or you are considering a reverse point, in both these cases, at least qualitatively, we are able to show that the derivative is identical. The value of the derivative that we are able to determine through this expression at least is qualitatively identical, and when you introduce this limit here, it will be quantitatively identical, meaning it will be exact value. So it is not that we have a definite description of the derivative. The description of the derivative can also be extended in this manner, wherein we are considering the a point that is less than the original point, a point that is behind the original point. It is not always the case. We have to consider a point that is greater than the original point. However, if we are considering a point less than the original point, there is a convention associated with it. The convention is always the free energy function of the forwardmost point should assume the first term in the numerator. Let me repeat. We have a generalized description for free energy, and this generalized description for free energy needs a point that is besides an original point. This point that is besides the original point can be greater than the original point or can be less than the original point. So when the point is greater than the original point, you have this description here. When the point is less than the original point, we have this description here. So whatever approach you adapt, you can either adapt this approach, or you can also adapt this approach. Either of these approaches will give you identical answers, provided you are introducing this limit here. We have shown that qualitatively the value that we get from either of these approaches are identical. So qualitatively we have shown that, and when we are introducing this limit, we will be able to also quantitatively prove it. Secondly, when we are expressing the derivative in this manner, there is a convention associated with it, that is the free energy function of the rightmost point, the point that is towards you, that is the forwardmost, should assume the first term in the numerator. The free energy of the rightmost point should assume the first term in the numerator. So this is the convention that we need to adapt, and when we are adapting this convention, both these approaches of describing or estimating the derivative will give us the identical answer. Now this approach here is referred to as the forward difference approach, and this approach is referred to as the backward difference approach. So what essentially we have done is, from the generalized description of the derivative, we are now in a position to describe two different ways of a given derivative for a function. You can describe the derivative of a function using a forward derivative approach for a forward difference approach, or you can describe a derivative of a function using a backward difference approach. So this is forward difference description of a derivative. This is a backward difference description of a derivative. So in our introductory class, we introduced a generalized description for a derivative, and now we are able to show that it is possible for us to estimate or describe a given derivative using forward difference and also using backward difference. So even though these description of the derivative might appear to be rather trivial or insignificant, you will soon notice that these approaches are adopted to numerically calculate a derivative of a function. They play a critical role both in the analytical treatment and also, most importantly, in numerical estimation of a derivative of a given function. So with this different forms of describing a derivative of the function, I would like to wind this lecture up, and in the next lecture, in the subsequent lectures, we will see what is the numerical role played by this different description of a given derivative. But in the subsequent lecture, we will see how this type of description of a derivative would help us understand a certain derivation or certain derivatives that we are familiar with. So we are familiar with derivatives, we have understood, or we have rather memorized several formulas. Let us in the subsequent lecture see is there any way for us to relate this generalized description of the derivative to our well-known derivative axioms. So that is where that is what we will consider in the next lecture. Goodbye.